Good morning. Let's start today's session. The morning first speaker is Professor Satoshi Tsujimoto. It is his second talk on extensions of discrete to the lattice and their application to box-ball system. So please.
Thank you so much. And I would like to thank all the people who attended to my talk. And in my previous talk, I talk about box and ball system can be described by using the KdV equation, which was some nonlinear partial differential equation. And also, it's not exactly described. Some related to the KdV equation or this type of Toda equation. Toda, this is already discrete one, but we already know about this discrete Toda related to some computation of eigenvalues. So here I show how relate. It's very close to this box-and-ball system. Okay. Yes. Oops. Yeah. In KdV case, already I show you this is some solitary wave has some interaction, but the shape will not be changed before and after. This is a feature of soliton. But this is same as box-and-ball system, also same property. But you see, in Toda case, this is the numerical computation, which were starting from some three-diagonal matrix, can be converged into these types. So in some sense, this box-and-ball system, we can see that which also describe some global behavior of eigenvalue systems. So you see some sorting property also appear in this eigenvalue computation. Okay. So, and also I want to stress how the difference between KdV type equation and Inoue Toda on finite lattice. So usually the KdV has on the infinite lattice, they have some soliton solution. Of course, there are several expressions for soliton equation, but the most famous one is in terms of causality determinant. In this case, the determinant size is corresponding to how many number of solitons appear in this initial setting. So it means that the soliton number will not be changed during the time evolution. So the soliton solution, the causality determinant the determinant size will not be changed. But in case of the Toda on the finite lattice case, so you see this is a Hanke determinant. So it is related to the orthogonal polynomial system, and n is just coincide with n corresponds to the degree of polynomial. And Hanke determinant, size of Hanke determinant could be changed. So gradually, so if n goes increase, then degree of determinant, Hanke determinant also gradually increase. So this is the big difference between them. Okay, now we are also, previously I also just remind you the ultra-discrete limit has been introduced. So this is the way how to use this ultra-discrete limit, but anyway, we will use this ultra-discrete limit. So here some a plus b will be goes to the minimum or maximum a comma b, and a times b goes to the a plus b, or division also minus sign. This is our ultra-discrete limit, which will be used later. Okay, so also we already have some introduction of how to non-autonomous discrete Toda will appear from the theory in the theory of orthogonal polynomial system, actually yesterday. But here, yeah, we start from some spectral transformation for orthogonal polynomial system. So first relation is so-called the Christopher transformation, and the second relation is a Geronimus transformation in my talk. And then together with these two equations, we can obtain the three-term recurrent relation. Or inversely, three-term recurrent relation can be decomposed into these two type of spectral transformation. It's possible. And this is correspond to some decomposition of three-diagonal matrix into the upper biagonal and lower matrix. This is the meaning of this transformation. And then, okay, just so remind you, this is the, after taking the compatibility condition, we obtain this type of non-autonomous discrete Toda equation. Here, we pointed out that the ST plus 1 and ST, this is the some spectral transformation, which was under some condition, it's possible to take freely. Okay, and then, but in this case, in this expression, it's not so easy to apply the ultra-discrete limit, so we need some subtraction freeform of this discrete equation. So that is how to introduce this dependent variable. This is also possible to introduce by using the theory of orthogonal polynomial. So like this. So just shift it and delete some term, then we achieve another equation for three-term recurrence, but it's a kind of contiguous relations within three terms. And then this this coefficient gives us corresponding good positive dependent variables, and it's possible to write down in the ratio of some polynomial, orthogonal polynomial. And then we achieve this expression to the subtraction free form. But someone tell me that it's not subtraction free. So let's see the time relation form. It's possible to just relate them in this way. So here, of course, this is okay. And this term, our newly introducing some non-autonomous parameter will be some difficulties happen. But if we assuming this assumption, so S of t is non-positive, and also some monotonicity, like decreasing with t. And in this case, this term should be positive. And moreover, so st plus 1 could be larger or equal to the s of t. So in this case, it's possible to apply our ultra-discrete limit. So here is the way of ultra-discrete limit procedure. And each dependent variable, we have to introduce some exponential variable, like q to the capital P and small e to the capital E, like this. And q and e and d we know about these are positive value, and s. So in our assumption, this is non-positive, so we need to put minus sign here. And then s of t, capital S, can be introduced in this form, in this transformation. And then by taking the ultra-discrete limit, so you see, so already I show you how the original rational mapping can be transformed into some piecewise linear mapping like this. So plus binary operator can be transformed into minimum one. And here, so this is okay. Yes, if we want to calculate this value in a new ultra-discrete system, so this is plus, and the division will be minus, and should be here. And here is also d, and this is some value of +1. So we just changing this part can be converted to the st plus 1. Here, st minus 1 doesn't happen because of our assumption is monotonicity can be killed this s of t. Then we achieved this expression for as a non-autonomous ultra-discrete Toda lattice. Sometimes I said NU Toda lattice. And then after introducing this expression, we can check how to relate with some box-on-board system. Original box-on-board system, this S parameter doesn't happen. So what's the role of S? We want to check, or we want to see what's the role of this new parameter. And then, of course, so the meaning of Q and capital E and capital D are the same as before. Only appearance of a new S. And okay, let's see the meaning of the example here. So if we start from Q0, E0, Q1, E1, Q2 with these non-negative, this is positive integers. And then, firstly, we took this S parameter, S of 0, should be taken as plus infinity. So in this case, okay, let's check the previous expression. Here, if the S plus 1 is equal to infinity, plus infinity, then always the first term will be taken as the n plus 1. So S take as plus infinity means, so no, it should be same as the original Toda lattice. So just first, we took the same as the original box-on-box system. So in this case, of course, 5 is the Q0 is the first consecutive ones, length of consecutive ones. So 5 means 5, 1 is here, 1, 1, 1, 1, 1. And E0 is the number of empty box between first and the second one consecutive ones. Then here, 5 means 5 empty box, 0, 0, 0, 0, 0. Of course, here, dot means 0. And then 1, 1, 1, 1, Q to the Q1, and E1 goes to the 3 empty box, and 2 to the Q2. Okay, it's just corresponding to our initial binary sequence. And then applying the time evolution of standard box-on-board system means just move to the nearest empty box. So 1, 1, 1, 1. So all 5 should be just moved to here, and 3 to here, and 1 should be overpassing these ones, and then 1, 1. So same, and also next one also same, 1, 1, 1, 1. And the last 5 just overpassing to here, and this 1 should be go here, and 1, 1 will go there. And it's easy to say that this is the first 2 line or 3rd line is the same as original box-on-box system. But if the S2 is just our new, newly we have to take into account in this case. So ST, if of course after applying our non-autonomous ultra-discrete Toda, here is the result. So 4, 3, 2, 3, 4. So then you see that first, first please count the number of balls. So here, 1, 2, 3, 5, 6. So let's think about go look. 10 balls. Is it? 1, 2, 3, 4, 5, 6. No. 10 balls. But original first, but the initial binary sequence, 1 has 5, 4, 2. It means 11. So in this model, the particle preserving doesn't hold. So number of particle could be changed. So in this case, just reduced. So, and then the other, so at this moment also 3, 3, 3, 3, and okay, so what's happened here? So in this case, let's think about the size. The S of t means the largest maximum. So it should be the impossible to exceed the number of S of t. So this is in some sense this is the meaning of S of t. If S infinity, then nothing happens. It means that it's impossible to exceed the number of consecutive ones. This value S0. But in this case, here, for example, if we introduce some carrier rule, so pick up, usually we can pick up, but here, S4 is possible to interpret as a capacity of carrier. So already I explained what's the carrier capacity it is. And in this case, usually we don't touch at all, nothing to do. If the carrier capacity has already maximum capacity has happened. Then but in this case, pick up the ball and throw it away. This is happened. So then 1, 1. Okay, it's a 1, 1 and 1. Yes, yes. Here in this case 4. Up to 1 to 2. Sorry. Maybe I made mistakes. So no. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry. So from 1 to 2. Sorry. Here we already encountered.
We've lost a ball from 1 to 2.
Yes, 1 to 2.
In 1, S1 is already plus infinity. S1.
Yes, S1. The meaning of S1 is just before. I mean, using to compute this term. So S0 and S1 is not so. Maybe S0 will not affect the result. I mean, they just shift the meaning of S of t. And then it's sometimes happens. So sorry, I maybe better to miss, but here I just put it on. And anyway, from here to here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here is 11 balls. And in the t equal 2 case, already the number of balls has been reduced to the 10. So here we can pick up 1 ball, but this ball has been abandoned from this system. Then already 4 to 4 is happened. Okay. This is the meaning or interpretation of non-automatic ultra-discrete Toda case. Okay, and already, sorry, I already write down here in description. So time 1 to time 2, and also here I changed from the value of S of t from 4 to 3. Here also more severe size limitation has happened. So only size has been reduced to the 3. Okay.
But finally, will it all go away?
Yes, if we think about go down. So of course, it could not be survived at all. Yes. So and also already we have assuming S of t is monotonically decrease. This is our assumption when we applying this ultra-discrete limit. Yeah. This is, in some sense, natural in my mind.
No, but it could be S equal to...
Sorry, please.
It could be Sn equal to 3 for all n greater than 7, right? That could also be possible.
You mean S2 to the, for example, 7?
No, S8 equal to 3, S9 equal to 3, and so on. It could be 3 forever, right?
Yes.
That is also possible or not?
So you mean all 3?
Yes.
Yes, possible.
So then the number of balls will not go to 0.
No, not go to 0. So in each time, the carrier capacity has been fixed. Yeah. But so these 2 consecutive ones, or 3 consecutive ones can be possible to carry to the next shift.
Yes.
Then if the S7 is just constant, in this case 3, then these ones, the number of balls should be conserved, preserved.
No, but earlier I asked if it will happen that you will get all the balls vanishing.
Mm-hmm. So by...
In this system, in this example, what will happen in the limit?
In the limit means S of 7 is, we can choose freely, only assumption that decreasing.
No, but so, I thought Sn is evolving according to the dynamics.
Yes, but S of t can be chosen as a, is it?
S of t is arbitrary or?
Arbitrary, only. Yeah,
okay.
Assumption is just this one.
So there's no dynamics for S of t?
Yeah, S of t has no dynamics.
I see.
Because this is a shift parameter.
Okay.
In case of a numerical algorithm, it's possible to take arbitrary.
Okay.
Of course, some assumption exists.
Yeah, okay, but, I understand decreasing.
Basically, it's possible.
Okay, I see. Thank you.
Okay. It's negative or
Non-positive.
zero. Negative or zero.
Positive.
Yeah, non-positive, here I use as a, in this meaning. Because we want to take minus h could be positive value. So we want to assume this equality. In order to achieve this inequality, S, so this combination should be positive or zero.
S itself can be negative.
It's in our assumption, it's impossible.
Negative is possible.
Yeah, it's only negative possible. So by using this variable transformation, yeah, so we are using this variable transformation. This is a minus sign. Yes. This is, yeah, of course, this is some very, very confusing. So that is why I just pointed out this minus signs appear here. Anyway, already we know about the role of S of t in case of in our non-autonomous ultra-discrete Toda case. So also we can check or we can obtain the corresponding exact solution for ultra-discrete non-autonomous Toda. So of course here is a way to introduce how the discrete non-autonomous Toda has some explicit expression. So actually yesterday I explained how to derive from the theory of orthogonal polynomial. It's rather easy. So Q and D has this kind of expression. So I omit the definition of delta. This is a Hankel determinant of composed from the moment of orthogonal polynomial, the linear functional related to the orthogonal polynomial. And then, some sigma is also slightly shifted, but also I don't want to go into detail. But we know about how Q and E and D can be expressed in terms of moment. And okay, let's take ultra-discrete limit to this Hankel determinant itself. So here we can introduce, this is the same manner. So we can apply the ultra-discrete limit to the equation, but also we can apply to the equation, solutions. And of course, we need to check the positivity of solutions, otherwise useless, meaningless. And then, so from this level, it's easy to introduce the corresponding ultra-discrete limit. So just here we have only division or multiplication, which can be, division goes to minus sign and multiplication goes to the plus sign. Okay, it's easy. But how about the determinant itself? And then it's possible to write down the Hankel determinant or just shifted sigma and t can be expanded in this way. So we use the Binet-Cauchy or Cauchy-Binet formula. Then we can write down explicitly. So t is the, okay, sorry. Yeah, because here t is our time discrete variable. And each time we choose the s of t as a freely. So here we can put the s of t in each time freely. Okay, this is our solution. Just yesterday we introduced. And then after that, we can assuming some assumption to the s, and also w and lambda could be positive one. Otherwise, impossible to introduce this variable transformation. In this express transformation, we are assuming lambda j here. This is the eigenvalue of corresponding Jacobi matrix. And Wri is appear in the expression of linear functional, which was Gauss quadrature formula. This value also possible to explain. But anyway, our first assumption is these value should be some positive value. And then after introducing this variable transformation and taking a limit, then it's slightly we rearrange the old term, but final expression is this one. Maybe it's not so difficult. Is it? Okay, okay, sure.
Do you have any assumption to lambda Ri in before router discretization?
Not before. After, actually, lambda I and lambda j should be distinct.
Yes.
And some real value, or positive real value. This is our assumption.
I see. So because of that assumption, we get 2 times n minus 1 minus I, these coefficients.
Yeah. Coming from the...
I see.
Yes, yes. This is, which part can be... So I also here, okay, I maybe... So some, the order of lambda j, lambda 0, lambda 1, lambda 2, some order we are already assuming in this expression, sorry. In order to rearrange this to the expression, we are assuming if lambda 1 minus lambda 2 happened, which part is increase or smaller or bigger is known by noticing the indices. And here minus signs happen, but this is Van der Mondo determinant will give us this expression. So squared one is it's very safe operation. Not so no difficulties in the procedure of ultra discrete limit. Okay. Okay, but you see, from here to here, we are assuming S of t is only non-positive. You see. So this is our solution coming from the discrete, ultra discrete, and non-autonomous discrete Toda lattice. This expression happened, and this is a generic solution. And here, we are assuming S of t is non-positive. So it means that this is a plus value. So from here to here, it's no difficulty in applying our ultra discrete limit. Okay? Yes. So we don't need to assuming some monotonicity of lambda of t. In the equation level, we have to assume. But in this level, some mismatch has happened. So you see, yeah, the condition in this solution, ultra discretization, condition of monotonic trees for S of t is not necessary. So this fact means some positive ultra discretized solution exists. But our ultra discretized non-autonomous Toda is impossible to describe this solution. So in some sense, it means this fact suggests something. It means that the existence of some ultra discrete limit without using this monotonicity condition on S of t. Some good system might be exist. So we can introduce to another, in some sense, we can compute this flow of generality of S of t by using some modified non-autonomous ultra discrete Toda. So it means that we have introduced here, now we are doing some auxiliary independent variable k. And k and t are, so both of them are, of course, it's commutable because it's visible that both of them are. So here, the first one is our first assumption to derive the non-autonomous discrete Toda. But this second line and the fourth line is a new assumption for orthogonal polynomial P. And here, difference is choice of spectral parameter. The first one is S of t is ours. But our newly introducing time evolution step could be S parameter should be taken as a 0, only 0. And Also, you see, and in order, so with this direction, we can introduce the new independent variable, discrete variable k. So that is why we have to introduce the two upper indices for denoting the two-dimensional time space. And n is, of course, our base lattices. And then by introducing these new time evolution step, this is also a similar trick, which was appearing in the non-Thomas Toda case. So here we can introduce some two auxiliary positive dependent variables. In previous case, only one dependent variables only. So here we can introduce two types. So maybe we call A and B as a newly introduced dependent variable. So both of them slightly different. Okay, so this is, of course, it's a bit difficult to say why we introduced this quantity, but as a final result, this is will give us a quite good system to compute this our solution for generic S of t only. No Mondidici, we don't have to assuming. Is it okay? Just okay. Let's just we just introduce these discrete variable. Then what's happened? Let's see. Actually, we use the same manner. Previous time our compatibility condition only two linear equations, but in this case we have four linear equations. So we have many kind of compatibility condition, and also correspondingly we can obtain some compatibility, some nonlinear equation among these Q and E and Q bar and E bar and blah blah blah. But we can take from the appropriate equation from these among these compatibility conditions, and then we can pick up these 1, 2, 3, 4, 5, 6 equations for six dependent variables. Yes. Okay.
Are Q bar, E bar, and A new variables?
Yes. This is a previous expression for here Q and Q bar.
Yes.
And E and E bar.
Yes.
And dependent variable from A, this is B.
B is also new.
Yes, A and B.
Oh, I see.
New one. So we need to introduce two auxiliary dependent variable, A and B. Previous one is we said that we call that as a D variable, but in this case I chose to change the name because of the system is different. Okay, so we can introduce 6 equations, and then the trick after that, the rest is same manner, just taking the ultra-disk limit. So here, and also I would like to stress that in this expression, so A0 and B0 has this expression, and in this case, minus S happen, but here we also assuming the non-positive assumption. And it's possible to take the ultra-disk limit without monotonicity on S. So equation is like this one, and the minus the shift parameter S is appear in the boundary condition of A and B, actually. And then this value just goes to S of t, and capital S of t, and B0 kt is, so in discrete case, this one, but also this is easy to convert it to the ultra-discrete form. So just positive value happen. So not needed to introduce some monotonicity. So in this case, so we introduce Q and capital Q and capital E, and both of the bar decorated variable exist. And here we can compute the corresponding box of but we can observe the what's the meaning of these four dependent variables, Q, E, and bar Q and bar E. Okay, the original, the normal Q and E correspond to the standard non-autonomous Toda variable. So in this case, same time evolution has happened, of course. But in the case of the Q bar and E bar case, this is in some sense, this is a carrier capacity model. So S denotes in this case, exactly same as carrier capacity model itself. And then, so in some sense, it's possible to reduce to if we know about this time evolution, we can obtain this size limit evolution, just deleting. If the one is not moving, then we can abandon this one here. And then results should be same. Yeah, should be coincide. And in some sense, our non-autonomous ultra-discrete system has some special feature. And here, if in the level of Toda ultra-discrete Toda variables, then okay, so here now by using this modified non-autonomous ultra-discrete Toda, we can assuming this S of t can be not only the decrease, also we can achieve assuming the decreasing or increase and decrease freely. And correspondingly, the appeared number of ones should be changed like this. So this is the true behavior of non-autonomous ultra-discrete Toda, just I would like to say. And also in the level of equation, by applying the ultra-discrete limit, some important information will be lost like this. Of course, in the level, if original not ultra-discrete Toda if the information of ball has been lost, then it's impossible to recover to the original, or even the time reversibility doesn't happen. But in our case, so modified ultra-discrete Toda, possible to choose S as freely and also time reversible, so even this level. But in this case, we have to say that in the backstage, we know some extra information. How many number of balls has been thrown at some level. So this is, we have to remember. That is some auxiliary variable, which we have. So here, the ultra-discrete limit is a bit some troublesome procedure, especially the level of equation. So this in this example showing the totals some difficulty of this ultra-discrete limit, I think. Okay.
I'm a bit confused by the dynamics. So from row 1 to row 2, I understand S2 is 2, so you have killed all the extra boxes.
Mm-hmm.
But when you go when you went from 2 to row 3 to row 4, you've added one box to everything.
Yes.
Because S4 was 3.
Yes.
I understand that. But when you go from row 7 to row 8, you have increased S to 7, but you have not added 7 balls everywhere.
Yes. Because actually, this is not full of information of modified Toda. in the backstage,
Yes.
as some auxiliary variable exists, so which remember that this in the first consecutive ones, one ball has been abandoned in previously.
Okay.
It's memory, the system.
I see.
And then, so after that, of course, after 4 and 7, but this consecutive one doesn't growing more like 7 doesn't happen.
Does not happen.
Doesn't happen because not so many number of ball has been abandoned before. This is a memory.
But
Some
usually,
history, or I can say.
sorry, but usually, I mean, you started with 7, 5, 4. So at the end, you want 4, 5, 7, right?
Yes.
But this is 5, 4, 7. I mean, is that a typo? Or what? I mean,
Yeah, and under some, okay? Yes, okay. Yeah, this is maybe the first law already under some interactions.
okay.
Yeah.
But eventually it will become 4, 5, 7?
So of course, it depends on the first initial condition.
But the
Yes.
initial condition is
Actually,
this.
this is initial condition, but together with initial condition, we have some backstage.
Oh, the back's auxiliary initial condition.
Yes. So we need to be more precisely to be sure.
Oh, I see. So this is not full information.
Yes.
Okay. Okay.
It is. So this is quite confusing, sure, I agree. But anyway, this situation happened in our box-and-ball system. Okay. Then, okay, this is our basic model for ultra-discrete Toda case. But, and also related to the theory of orthogonal polynomial leads to our, such kind of BBS model. And then we know about, there are many kind of orthogonal systems. So let's think about some different type of orthogonal systems, so-called low-rank bi-orthogonal polynomial. And so many people know about from the low-rank bi-orthogonal polynomial leads to the some relativistic Toda equation happen. And it means that we want to introduce the ultra-discrete relativistic Toda type BBS. And also the story is almost same as the orthogonal polynomial system case. And, but of course, the first setting, what is the low-rank bi-orthogonal polynomial? This is the first setting, this is important, so I want to explain a bit slowly. And then you see, so we will start from a three-term recurrence relation. This is same, looks like same as orthogonal polynomial. But here, I want to say that this x, usually standard orthogonal polynomial, the monomial x will appear only this term. But here, the lowest the coefficient of Pn minus 1 depends on x. This x usually don't appear in the standard orthogonal polynomial system. But in case of the low-rank bi-orthogonal polynomial case, we can put this value here. And then this is previous standard orthogonal polynomial system correspond to the Jacobi matrix. A three-diagonal matrix should be appear as a eigenvalue problem. But here we can relate them in terms of matrix form. So Rp, P is some eigenvalues, eigenfunction, and X and L and P. So X is, in this case, plays role of eigenvalue. And, but here, R is upper bidiagonal, and the matrix L is lower bidiagonal matrix appear. So this is some kind of a generalized eigenvalue problem for matrix pencil R and L. And then P is generalized eigenvectors. And this P gives us a corresponding low-rank bi-orthogonal polynomial itself. And in this case, bi-orthogonality relation should be changed. And here, P and X is some nth degree of polynomial, but this degree of polynomial Pn orthogonal with to the x to the minus k. This is a low-rank polynomial system. And P and X, yeah, actually P and X is a polynomial just orthogonal to some set of Laurent polynomial sequence. So, but here I just saying this is a Barcelona relation for LPP. And then the linear functional space also we have to extend to the just for the from the polynomial space to the Laurent polynomial space to the L. Okay. And okay, so if the polynomial sequence satisfies this type of particular relations, then monopolynomial sequence called as a Laurent polynomial system with respect to L. This is our setting. So let's start from this setting. What's happened? Okay, it's of course this is the same manner. Sorry, maybe same. Okay, sorry. And then the discrete, so we will start from this one, and X could be the, so zero of characteristics polynomial of R and L. And X and P are generalized algebra problem for basic pencil L. And here, L is bidiagonal, lower bidiagonal matrix, and the diagonal term is 1, 1, 1, 1. So it's regular matrix. So it's possible to consider the inverse of operator. So let's introduce the X by introducing this matrix. And we can introduce this X, we can introduce some similarity transformation very close to the Toda case. And X goes to the X star by using this bidiagonal matrix of L. And this, similarity transformation leads to some discrete time evolution, and which was just which will give us a discrete relativist Toda lattice is happened. Okay, so yeah, in this case, P and X is defined like this. So, so you see, P and X is a standard. In this case, if we write down in this way, the eigenvalue system is standard eigenvalue problem, but the matrix is not tridiagonal or bidiagonal. Should be Hessenberg matrix should be appear. And then characteristic polynomial is the definition is exactly the same. And then this similar transformation leads to this expression. Then we can equate the element y3. Then we will obtain this expression. It's quite, it's a very simple expression. But this is a truly relativistic Toda lattice, discrete one. And then we can also say, this is also same manner. So just introducing the dependent variable for positive one as f is in this case q plus e. And this is the expression for dependent positive one. This is the discrete relativist Toda lattice in subtraction free form is given like this one. Okay, same manner. Oops, sorry, maybe I made some mistakes. And then we can introduce the corresponding relativist ultra-discrete model. So this is our discrete one. And by applying, so I just omit the dependent variable transformation. But from here, capital F to, from F to capital F, and plus sign goes to the minimum operation, and Q to the here, and plus minus, yeah, and plus. Oh, it's a. I think that it's just a simple operation. Will give us this one, and then we will obtain this binary time evolution has appeared. So I would like to showing in Blackboard that how to explain in oral rule. 4 consecutive ones and 5 zeros. And 1, 1. Okay. It's rather complicated rule has been appeared. But in this case, it's not so difficult. So let's make a wall here. So it means that I divided it into subsequence. And then let's think about only this subsequence. So in here, just same as box and ball system. And here is also. But this box and ball system only work on within the subsequence. So in this case, some one has remained as impossible to move to the inside within this subsequence. And then this one should be moved to the here with box. With box. And then the last one should be moved to the here. And then maybe you will already notice that maybe then this could be 0. Okay. Well, maybe not here. And this one will be moved to here. So together with ball, together with box. And then 1, here is 0, 1, 1, 0, 0, 0. Okay, is it correct in my slide? Okay, I'm slightly nervous with this one. Anyway, this is okay. Oh, maybe one more times. Is it okay? Yeah. So just divide it. Divide. And in this case, within the subsequence, only 2 balls can be moved. And then, okay, let's firstly write down. And then the remaining ball and box has been here. And this will be moved to here. So just move to the next subsequence. So next subsequence after the first ones, move to this is the position. Then you may notice that, okay. Yes.
And why there's one more 0 after the 4 ones? There used to be 5 zeros, right? And now you've replaced the 4 first zeros by 1s, okay? So then there's a 0, but why are there 2 zeros here? So the 0, which is at the end.
So 0, 0 happened.
So
0, 0.
I see.
And this one is just, okay, let's, yes, yeah. It's a bit difficult. So, and 0 correspond to here,
yes.
Correspond to here.
Okay.
And this one correspond to here.
Yes, because
okay.
missed. Okay.
This such shift will be happen. Okay. I don't need to one more times. Maybe just I write down already. Okay, 0, 0. So this was being absent. 1, 1. 0, 1, 1, 1, 0, 0, 1, 1, 0. Okay. Yes. Yeah, it's not so bad, but a bit complicated because of we have to move the ball together with box. This situation doesn't happen on previous box and ball system. But in our case, in our, relativist Toda can give us such type of box and ball rules. 何時まで
But in this case also, if you start with 4 to 1, do you end up with 1 to 4 at the end?
Sorry? This one?
Yeah. Does the soliton behavior
Yes.
hold?
It is. It is.
So at the end, you will get 1 to 4.
Yes.
I see.
And such sorting property will be easy to check in terms of solutions. But here I omit the how this expression has happened. But we know about corresponding orthogonal polynomial theory for Laurent bipolynomial, which will give us exactly just coincide with almost same as this same discussion can be done for LBP.
Can I ask?
Okay.
Maybe you will give explain that. Is there any conserved quantity?
Yes.
Oh, nice.
Of course.
Okay.
Of course. Why not? Yeah. Anyway, yes, and maybe it could be very close to the Professor Geftman's research work, and this Laurent bipolynomial system. So it was upper diagonal and lower bidiagonal. So matrix pencil can be transformed to each other with orthogonal polynomial system. It's a Jacobi matrices. And how to understand from these discussions. And we will start from we have started from some spectral transformation for LBP. But in some sense, it could be, so this is our standard three-term recurrence for LBPs. But by using 1 and 2 in this way, we can achieve this type of three-term recurrence relations. Maybe something, yeah, okay. This is not three-term, this type of relations. And then if we can introduce this type of variable transformation. Oops, okay. Then, okay, I maybe miss some part, but as a final, sorry, I have only 2 times, 2 minutes. After some computation, by introducing this type of transformation, so K, the upper strict means some time evolution. So if this time evolution step could be, depends on lattice number n, like this. And then we can introduce a new variable, Q hat, or E hat, and P hat. So Pn is some nth degree of polynomial, and Pn hat also nth degree of polynomial. But different choice of nth degree of polynomial in the many number of time evolution step. We have each time step we have some dependent some polynomial system as eigenvalues in LBP, and by choosing with this way, this Pn hat has this expression possible to possible showing from 1 and 2 we can obtain this type of relation for P hat. So T hat has composed from the product of L hat and R hat. So this is nothing but a standard Toda lattice, Toda chain. And this explained how Laurent bipolynomial polynomial can be related to the standard orthogonal polynomial system by using this type of independent variable transformations. So it means that we choose take the coordinate. Maybe this has basically done by Professor Geftman, I think. Is it true? I think you know this phenomenon. Okay. Yeah. Maybe. Maybe next on my last talk, I will try to introduce the bit complicated, more intriguing scenario for the epsilon bi-orthogonal Laurent polynomial. This is for next talk, my topics, and which was firstly introduced by Faber Bissi and Geftman, and actually. They don't name this orthogonal polynomial system, but we just call that epsilon Barson-Roland polynomial in our talk. And then I will show you the corresponding box-and-Ball system, how showing. Of course, in this case, a bit complicated than Roland polynomial. So it means that a bit complicated than this one. So let's think about, I'd like to explain what happened in this case. Okay, maybe just time has come. Thank you so much.
Thank you. Is there any questions or comments?
I mean, we know many examples of classical orthogonal polynomials. Is there like a well-known example of this Laurent biorthogonal polynomial family?
Yes. Actually, this Laurent biorthogonal polynomial can be treated as an orthogonal polynomial on the unit circle, LUPC. So in this case, you know, the many number of very well-known classical orthogonal polynomials already known. So actually, I'm very familiar with these topics, and I also try to introduce several classical some kind of exceptional generalization of this type of polynomial system. This is my another major research work.
Other questions? Okay, I'd like to ask a question. So, will you show the Lux pair for the relativistic Toda tomorrow or on Sunday?
Today?
On Friday?
Lux pair.
Lux pair for relativistic Toda.
Yeah, this is the, maybe, yeah. I omit some detail, but actually, in more, maybe on Friday, I will show you some setting. But anyway, it's not so difficult.
I see.
Yeah.
Thank you.
Maybe, yeah, this one. Yes, sorry. 1 and 2. This is the Lux pair. P is the eigenfunction. And this is a px plus 1, so yes.
I see, I see. So we can construct conserved quantities from this one
Yeah.
by taking ultra-discretization.
I hope so. Actually, for the case of, for the ultra-discrete system, we need to be careful with how.
Yeah, but if the positivity works well, then it's
Yeah, I think so.
automatical.
Yes. Maybe you're right.
We'll see.
Yes.
So, okay, let's thanks Tsujimoto again.
Thank you so much.